Hydrology, Unit Hydrograph Method, Chapter 9, Lecture 2. I'm Dr. Marty Matlock. This is probably the most confounding concept for most hydrologists, and it's not that hard. Let's get to it. Remember, the role of the hydrologist is to anticipate and predict rainfall and runoff phenomena. It's complicated, but it's not that hard. So we understand our water balance, Q equals P minus ET minus infiltration minus delta S, which is to say Q equals precipitation minus initial abstractions. And we understand that there's a time phenomena associated with Q, that runoff events occur over time because the precipitation events occur over time, and that the conditions in the watershed determine the rate at which water runs off. We also understand that if we simplify the model, that the process can be standardized if we have a common area and common land covers and characteristics. If our initial abstractions are common and our lengths of travel are common, then Q as a function of P should be relatively standardized. We've talked about runoff hydrographs, that is, the amount of runoff that occurs over a period of time. We explored natural runoff hydrographs. We've simulated runoff hydrographs using the SCS curve number and the rational method. And we looked at the USGS regression approach as one dimensionless approach to developing hydrographs. Now we're going to explore the unit hydrograph method, which is an extension of unitless or hydrographs. And unitless hydrographs are not that complicated. We complicate them because the mathematics can become quite involved. But the conceptual framing is not that difficult. Instead of looking at Q, we look at Q of an area over total Q. And instead of looking at T, we look at T as a function of time of peak. So that's all this comes down to, is we standardize everything. So the y-axis is 0 to 1, proportional, where total flow is a function of flow for your area. And then time is proportional to the time of peak. So your time of end is a function of how long it takes to get to time of peak. So time of peak is by definition kind of set to 1. And so T over TP means if you've got a 4.75 T over TP unit time of events, of runoff events, that means it's 3.75 times time of peak before the runoff curve goes back to the base flow. That's simply all we're talking about. Q sub P is the flow of peak, and of course Q is the flow that you observe in your phenomena. So we're standardizing everything. We've done this before. This is not new. The unit hydrograph is dimensionless direct runoff hydrograph, DRH. I know we like our acronyms. Resulting from 1 unit of excess rainfall, 1 intracentimeter. And it was originally developed by Sherman in the 30s for time, 1 hour of rainfall. It's become really about 1 intracentimeter of rainfall. That's the unit we're talking about these days. We use theoretical unit hydrographs in order to simulate what an observed hydrograph might look like. Because these are for case 5s when we have no data in our watershed. No rainfall data, no runoff data. So we have to extrapolate everything. It's very similar to synthetic storms, where the entire duration of events is allocated across a proportional timeline from 0 to 1. So we have proportional flow from 0 as a function of peak flow from 0 to 1. So flow here 0.7 is 70% of peak flow. That's all this means, 70% of peak flow. So you take the flow of your hydrograph over a synthetic hydrograph of Q over QP. And the time is all proportional to time of peak. Time of peak is set to 1. Flow in a dimensionless hydrograph has the same allocation of proportional flow per unit time, 0 to 1. So the unit hydrograph is a direct runoff hydrograph from 1 unit, 1 inch per centimeter, of effective rainfall, that's precipitation minus initial abstractions, occurring uniformly over the entire catchment at uniform rates for a specified duration in time. Well, we know that never happens, but it's an assumption we make to simplify our calculation of a unit hydrograph, and it's effective for most purposes. That means you don't really work with huge watersheds, because huge watersheds ought to have a gauge station. It's based upon a Qmax for a specific return period T. And we can calculate those now using the regression method. We have explored 4 methods for finding Qmax: observed data, SCS curve number, rational method, USGS regression method using stream stats. All we need is a rainfall duration of a period D. If we know what the effective rainfall is, so that is the rainfall that results in runoff for a period of D, and we know Qmax, we can build a hydrograph. That's the whole thing behind a unit hydrograph. Now, it makes a number of assumptions. The XX rainfall has a constant intensity within the effective duration. We know that's wrong, but we assume it. The excess rainfall is uniformly distributed throughout the whole drainage area. If your drainage area is more than an acre, we know that's wrong, but we assume it. The base time for the DRH, the duration of direct runoff, the direct runoff hydrograph resulting from an excess rainfall of given duration is constant. The ordinates of all direct runoff hydrographs of a common base time are directly proportional to the total amount of direct runoff represented by each hydrograph. And for a given watershed, the hydrograph resulting from a given excess rainfall reflects the unchanging characteristics of that watershed. Which is to say, you can't develop a unit hydrograph today and then 10 years from now use the same unit hydrograph if 30% of the hydrographs become housing development. You got to develop a new unit hydrograph. Conceptually, it's a simpler linear model of runoff from rainfall, where effective rainfall is constrained to 1 unit. So if we look at input, and if we have precipitation of input to the system, and then output, Q sub n, if n is less than m, then the total flow equals the sum of the precipitation times the unit hydrograph characteristics minus m plus n over m equals 1. Simple enough, right? Another way to look at it is this. Here's your watershed in a bucket. Watershed in a bucket, rain falls in that bucket, water runs off. The water that runs off is Q sub n, the rain that falls in is P sub m. The unit hydrograph number for a unit pulse input, 1 centimeter of rainfall over some amount of time. It takes some amount of time to get this. This delta T is not defined. This delta T floats. So if it takes an hour to get this 1 unit of rainfall, which is usually an inch, or if it takes 5 hours, it doesn't matter. That's your unit. That's your delta T. Gives you a discrete pulse reaction to the system of effective rainfall. That means that all the rainfall that occurred before that didn't run off doesn't count. It's only the only pulse that counts is what occurs. So here, if we look over at what this means in a unit hydrograph, this is all, by the way, from Chow, Maidment, and Larry. An incredible resource. You should buy it if you can find it. It's out of print, but you need to find it in your used bookstores. Go to Amazon. It's a critical reference for any hydrologist. Chow et al., 1988. So anyways, look at 1 inch or centimeter of rainfall excess for some delta T gives you a unit hydrograph of duration delta T. And remember that how long this runs is a function of delta T time. This equals 1 delta T change this time over whatever, and it could be 3.5, 4. And the peak flow equals 1, 2 as well. So if we look at this as a S curve, we look at the unit step input, gives us unit step response. 1 inch of input gives you some response to the watershed. If we look at this from a perspective of cumulative flow, not cumulative flow, but pulse flow. Pulse flow, you have a unit of impulse, an impulse response. 1 centimeter of instantaneous excess rainfall gives you a unit hydrograph. That's what we're seeing here in item 2, and the same thing in item 4. So the system starts from rest. Direct runoff starts from 0. All previous rainfall is absorbed by the watershed. initial abstractions are lost. So it starts from 0. So that's where rainfall starts. The system is linear. Direct rainfall runoff hydrograph is calculated using principles of proportionality and superposition. There's no weirdness going on here. Transfer function has constant coefficients. That is to say, the watershed response in time is time invariant, not changing from one storm to the next. A storm today is the same as a storm in August, is the same as a storm in December, is the same as a storm in March. The system obeys continuity. That is, change in S over T equals I times T minus Q times T. That is to say that the total depths of excess rainfall and direct runoff are equal. Mass is neither created nor destroyed. Water doesn't disappear. It evaporates, but that's not disappearing. That's just changing state. And those are all part of the initial abstractions. So the rainfall that really occurs, the P sub M, equals Q sub N. When you add up all the moments of P sub M and all the units of Q sub N, it's the same volume of water. Those are critical things. These are fundamental principles in engineering. Continuity of mass, continuity of energy. Continuity of mass is the key here. The primary variable being predicted are time of peak flow, T sub P, that's this delta T, time of inflection of the receding limb, that's about here, midpoint, time to return to base flow, that's this point. Total runoff for a unit hydrograph for a given watershed is equal to watershed area times unit depth. If the effective rainfall, P minus initial abstractions, is 5.5 inches, Q equals 5.5 inches times the watershed area, which is a function of cubic inch or square inches, which gives you L3. Watershed area is L2, but inches times area, it gives you L3 volume. We know that. So once you have a unit hydrograph, let's say you've developed a unit hydrograph for a given rainfall event with an effective rainfall of P net, that's the net precipitation of any intensity, inches or centimeters, we can convert to a unit hydrograph. So we take any rainfall event and we can make a unit hydrograph out of it by dividing P net by P net equals 1. That's the cool thing, is we standardize the thing. We can divide Q for each increment by P net as well. This concept of proportionality is the basis of the unit hydrograph. The unit hydrograph is constructed by building columns of runoff using a time lag for each unit of effective rainfall. The unit of rainfall running off each time lag period is added to the previous runoff, and a curve is constructed. So here we have 3 periods of rainfall. M equals 3, M1, P1M, P1, P2, M2, P3, M3. And so here's the unit of runoff that occurs for P1. Here's the unit of runoff that occurs for P2, P3. But it keeps coming on because the runoff doesn't stop when the rainfall stops. It lags out. And so we get this, based on observation of data, we can see that we have a pattern of allocation of runoff. And then we can allocate that for each increment. So it's P2, we have runoff, rainfall and runoff. P3, we have rainfall and runoff. And we can add those up. So here's our P1 curve, here's our P2 curve, here's our P3 curve. And notice what happens is the start of the P2 curve is 1 increment over from the start of the P3 curve. P2 curve doesn't start till 1 increment of time has passed. P3 curve doesn't start till 1 increment of time has passed from the P2 curve, right here. There are a number of ways to see this. We'll explore those. Conceptually, it's not hard. Yeah, it looks hard. Excel makes it easy. So let's assume we have this data set where we have duration of a 1-hour storm event with time in 30 minutes. And we have an area of the watershed that's 228 acres. We have a base flow of 10 cubic feet per second. Effective precipitation, of course, we already have all the data in black boxes are given to us. So we have runoff. We have a Q sub T for event over 6 increments of time. This would be 6 hours of time before the runoff returns back to a base flow of 0. So if we look at, this is all given to us. This is all stuff you would take from a rain gauge in a watershed. So the flow of direct runoff is We start with 0, and we subtract base flow, 10 cubic feet per second. So 27 minus 10 is 17, 39, 110, etc. So we subtract our unit of base flow. That gives us QDR. Now, the volume in terms of inches is just simply this divided by the watershed area. And that tells us how much of the volume of rainfall has been allocated to this system. The unit hydrograph equals QDR minus the total VDR. So we subtract these, and this gives us a unit hydrograph of flow as a function of 1 inch. We basically converted this 2.14 inches. We divided, so all of our rainfall is 2.14 inches. We divide this by 2.14 inches. And that's how we come up with these numbers. It's not complicated. Unit hydrograph equals the QDR, which is our effective runoff, minus, sorry for the spelling error, minus the total of our rainfall, 2.14 inches effective rainfall. And so we've standardized, we've made this equal to 1 inch of rainfall. So this is what, if we had 1 inch of rainfall, this would look like. Now we have a unit hydrograph. So this column is key because this column now is our map to a unit hydrograph for 1 inch of rainfall. And what that looks like for runoff for a very specific set of data, real data converted to a unit, by simply taking the real data minus base flow divided by the total amount of rainfall that led to that unit hydrograph. This unit hydrograph can be applied to any storm of any duration and intensity for the watershed to create another hydrograph. So the S hydrograph method is a cumulative hydrograph constructed from individual rainfall unit hydrographs of effective precipitation duration T sub I that generates uniform runoff. So we have a centimeter of runoff, let's say an inch of runoff in some time T sub I, which happens to correlate, which we make correlate with Q sub P. And T sub I is the time for 1 inch of effective rainfall. You want a hydrograph for 6 inches. You add 6 of these together. How do you do that? Well, T sub I occurs at Q sub P. Add the cumulative volumes of water. You add another T sub I, that's 2 inches of rainfall. Add a hydrograph. It starts at the beginning of the end of the first one, at Q sub P of the next. Add another, add another, add another, add another. Now we have 6 rainfall hydrographs. And what you do is then you start adding up the numbers. This is runoff, Q in cubic feet per second at the peak, and we start adding more. And then what you end up with is a cumulative flow curve, an S curve. And that S curve is simply a product of adding all these together. What makes this cool is in a spreadsheet, this is easy. This is just staggered columns in a spreadsheet. Conceptually, you can see it. Mathematically, you can do it very easily in a spreadsheet. It used to be harder than this, like everything else. So, we have our unit hydrograph calculated for our 228-acre site, whatever that site is. I made it up. Let's say we have a peak flow of 140 cubic feet per second and a time of peak of 2 hours. So lag time equals time of peak minus D over 2. That's definitional. Time of peak equals time of peak. The D sub 2 is the duration of the rainfall. And the duration of our rainfall is 2 hours, right? Or 1 hour. So D sub 2 is half an hour. So T sub peak is 2 hours. Time of lag is 1.5 hours. And their time intervals is 30 seconds. So every 30 minutes. Every 30 minutes we get another flow. Remember, lag time is here in hours. So the middle of our duration of our rainfall to the peak of flow is our lag time. Delta D is simply the duration of the rainfall that leads to the runoff. T sub C is from the end of the rainfall that leads to runoff to the point of inflection. Hard number to come up with, but we can calculate it. T sub P is easy. From 0, the time of the rainfall, to the time of peak. T over T sub P makes this thing uniform. Q of A of our system over Q is easy, or Q over QP is easy. Q of P is time of peak. Easy enough, and we've got our unit hydrograph data. Let's put this in a spreadsheet and see what it looks like. So let's say what would be a unit hydrograph for a 3-inch rainfall for our unit hydrograph in 2.5 hours be. We don't know Q sub P. We don't know T sub P. We don't know T sub L. We know D is, let's see, T is 30 minutes. So a 3-inch rainfall in 2.5 hours. Let's take a look. I think I got this wrong. I don't think we know D either. So here we have a half hour up for a 3-inch rainfall. This is the precipitation we got. It's all we know about the site. For this precipitation, for this range of precipitation in 3 hours, based upon the unit hydrograph, what's a hydrograph for our site look like based upon the unit hydrograph we built? We take the unit hydrograph we built, which you're familiar with, T, QT, nothing changed there, and we calculate T over T sub P. All right, so how do we come up with T sub P? So what we have to do is we have to finish proportionalizing our unit hydrograph. I'll back up a few slides. We're on slide 14 now. We back up all the way up to this, all the way up here. So here's our unit hydrograph we developed. It's really not a unit hydrograph yet. It's just a hydrograph for a particular storm event. But if we're going to make it a unit hydrograph, we have to convert the units of the X and Y axis. And that means we have to standardize these. So it no longer goes from 0 to 160. It goes from 0 to 1 in terms of peak flow. And it no longer goes from 0 to 6 hours in time. It goes from 0 to X times the time of peak flow. So if a peak flow occurs at 1 hour and it goes to whatever. So here a peak flow occurs about 2 hours. So our time of peak here is 2 hours. That's our best estimate of T sub P. So we go back to our to this system. So we assume that T sub P equals 2 hours. So we take time and divide by 2. So every half hour is now 0.25. So 1 is 0.5 because we're dividing by 2 because our hydrograph we built our unit hydrograph from had a time of peak at 2 hours. It said that for an inch of rainfall, it took 2 hours for peak flow to occur. And that's what we're doing here is we're standardizing this to that condition of the watershed based on initial abstractions and actual physically monitored flow through that watershed. So we also have Q sub T then is a function of runoff from our unit hydrograph, and QDR is, so direct runoff is QDR, and that's just, we assume 10 cubic feet per second base flow. So this should be familiar too. It's what we had in our unit hydrograph. So we need to calculate the total volume of direct runoff in inches for our observed hydrograph to convert it to a unit hydrograph. And so we take the volume of direct runoff in cubic feet per second here, and then we convert it into inches by multiplying it by the appropriate variables to go from cubic feet per second to inches over over the area of land, 228 acres times the square feet per acre. Divide all of that, and we end up with inches of rainfall for each time step. So this is the effective conversion of inches of rainfall for each time step. So at half an hour, there was some precipitation that resulted in runoff, 0.27 or 27 cubic feet per second. We don't know what that precipitation is. Well, this tells us it was 0.04 inches. That's what precipitation was necessary of effective precipitation to give us 27 or 17 effective cubic feet per second rainfall. So this is our effective, this is basically our rainfall event that it took to give us this effective runoff. This is the observed runoff minus its base flow, the effective runoff. And altogether it was 2.14 inches. Well, this is, we have to divide all of this by 2.14 in order to get 1 inch. So we take the QDR, this information, divided by the total 2.14, and that gives you the volume of rainfall it takes to produce 1 inch of runoff, which is to say the amount of runoff you get from 1 inch of effective rainfall. Let's say that again, because I think I messed it up. This gives us now cumulatively 459.8 cubic feet of water running off this site over the time period we have, 3 or 6 hours. And over that time, we had 1 inch of rainfall. If we take QA over Q, we now have the amount we can distribute all of that rainfall under a uniform curve. So now this uniform curve goes theoretically from 0 to 1, and over the cross the bottom theoretically from 0 to however long the storm lasts. And this tells us for 1 inch rainfall, the storm lasts 3 times time of peak. So a storm with a time of peak of 2 hours runoff lasts 6 hours in our watershed. Now we take all of this data for the unit hydrograph, this 0.017, 0.039, 0.11, and we lay it out with our time steps, 0.5, 1, 1.52, all the way to 6, and each of those, and we make a table with these columns. That's our next step. Now this is tedious, but it's not that hard. So you end up with a table with these columns. And then we add the precipitation that we have from our rainfall event. We know that we're given precipitation for a particular rainfall event. And the precipitation is that it's 1.25 inches in the first half hour, 0.75 in the next half hour, 0.4 in the next, 0.4 in the next, and 0.2 in the next. We know that we have 150 CFS base flow for this system, and it occurs over 6 hours. So here's our 6-hour rainfall event. We have 3 inches of rainfall over 1.5 hours. That gives us runoff over 6 hours. And we know our time of peak was 2 hours. So now we take this rainfall event and we multiply it times this proportional number. This rainfall event, multiply it times this proportional number. This rainfall event, multiply it times this. This rainfall event, multiply it times this. We multiply these to come up with these numbers, and we do that all the way down, copy and paste. Then we move down one step and we do the same thing here. Then we move down one step and we do the same thing here. We move down one step, we do the same thing here. Down one step, all the way down to the bottom. Then we add all of these up all the way across to see what our cumulative incremental rainfall events are. And lo and behold, they add up to 3 inches of rainfall. All we've done is we spread this 3 inches of rainfall out according to this distribution. We've made the 3 inches of rainfall fall in such a way that it creates a runoff event that looks like this. That's all we've done. Then we multiply, so this is how many inches. Then we have our direct runoff event, and we multiply this times 2.9, or we multiply this times our area to get our direct runoff in cubic feet per second, because we have rainfall, effective rainfall, precipitation E, times our area of our watershed, and we come up with cubic feet per second, and we subtract the base flow to come up with Q sub E, the effective runoff over time. Now 41,382 happens to be 41,382 happens to be what we get when we multiply 3 inches of rainfall times our watershed area. This gives us, now we graph this, and we have an effective rainfall event. We've taken our base flow out. If you want to do a real base flow, add 150 to the bottom of this, and we see what a 3-inch rainfall event for our watershed would look like, with a time of peak at about 2.5 hours. And you can see the relationships are fairly clearly defined here. We now have a runoff hydrograph with a peak flow right under 8,000 cubic feet per second that we can, at 2.5 hours, for a 3-inch rainfall event over the time period we're talking about, over 1.5 hours, which is an extreme rainfall event. So now we have simulated a runoff hydrograph based upon information from a unit hydrograph and a synthetic rainfall event, a potential rainfall event. That's the way we create a hydrograph when we have no data. Case 5. Oh, it's tedious as all get out, and it's complicated, and you'll have to watch this video 3 or 4 times over, and I'll share the PowerPoint with you as well as the Excel file, and so you'll have to sort of fumble around through it and get comfortable with it. Yeah, that's the problem with proportionalities. They're not complicated, they're just tedious. Well, we're engineers. TDM is our game. That's why we get paid the big bucks. You can watch a number of unit hydrograph explanations. Given what I provided, and perhaps the support of a number of other talented professionals out there, you'll get this and internalize it. Guess how the best way to internalize any complex system is? Do it. Practice, practice, and practice again. There is no substitution for doing. And believe me, this week we're going to do. Thank you.